Dubai already produces an astronomical volume of fresh water directly from the sea. But right now, the city is engineering an even larger water-making machine. If the current desalination network already processes hundreds of millions of gallons every single day, it raises an immediate and critical question. Why does an infrastructure system this massive suddenly need to get significantly bigger? And more importantly, when a desert metropolis extracts that much fresh water from the ocean, what exactly happens to everything that gets left behind? Solving water scarcity on this scale is an incredible engineering achievement. But the paradox of this technology is that the larger the engineered solution becomes, the heavier its secondary consequences get. To understand exactly where Dubai's water infrastructure is going, you first have to measure the sheer scale of where it stands today. By the 30th of June 2026, the Dubai Electricity and Water Authority reported a total installed desalination capacity of 555 million imperial gallons a day. That is an immense volume of water to pull from the ocean. It is generated largely through heavy industrial processes like multi-stage flash distillation, which essentially boils vast quantities of seawater, supplemented by seawater reverse osmosis. This infrastructure operates relentlessly, day and night, to keep a heavily populated desert environment functioning. But the surprising thing about this system is not that Dubai desalines seawater to survive. The surprising thing is that after building a daily production capacity of 555 million gallons, the city is still accelerating its construction. That number is no longer the ceiling for Dubai. It is simply the new baseline. Utility planners are currently engineering massive new additions to the grid, preparing to push the limits of coastal extraction to secure the next decade of growth. If a city already possesses one of the most capable, high-volume water production networks currently operating anywhere on Earth, you have to ask what kind of physical and economic pressure requires building an even larger one. A desalination plant does not exist in an isolated vacuum. It is physically tethered to the city it serves, and its output must match the realities of urban growth. The existing water machine is not being expanded because the old plants suddenly stopped working. It is expanding because the city it has to support continues pushing outward into the desert at a rapid pace. Every new villa community, luxury hotel, and commercial district requires a permanent, uninterrupted flow of fresh water just to remain habitable. Fresh water means functional showers and climate control in residential towers. It means active kitchens in massive resort complexes, sanitation in expanding hospital networks, and irrigation for extensive landscaping projects across the metropolitan area. This demand is not an abstract concept. It is a strictly measurable physical requirement. Over the 12 months ending on the 30th of June 2026, the Utility Authority reported an increase of more than 72,000 customer accounts. That represents roughly a 5.6% jump in a single 12-month window. These numbers translate into actual homes, commercial businesses, and residents drawing on the pressurized grid every single day. The water machine must stay ahead of that human threshold. It cannot simply produce enough supply to barely meet today's consumption. It must guarantee the capacity for a much larger, much denser urban footprint in the future. To meet that escalating pressure, Dubai is not just adding a few more pipes to the legacy thermal system. It is fundamentally changing how it acquires its water on a massive scale. Dubai's next answer to this growth is already rising beside the Arabian Gulf. That answer is Hassian. The Hassian Seawater Reverse Osmosis project represents a massive technological shift in how Dubai secures its future water supply. With a total projected investment of roughly 3.377 billion dirhams, this facility is designed to push the boundaries of modern coastal engineering. Once all phases are completed, which is scheduled for the first quarter of 2027, Hassian is expected to deliver approximately 180 million imperial gallons of water a day. But this project is not just about adding raw volume to the grid. It is about changing the underlying mechanics and efficiency of the city's survival. Historically, Dubai relied heavily on thermal desalination, an energy-intensive method that essentially involves boiling vast quantities of seawater to capture the steam. Halcyon relies entirely on reverse osmosis, and it is being integrated with clean energy sources to help drive down the enormous power requirements associated with making fresh water. The physics of reverse osmosis are highly efficient. Seawater is pulled into the intake pipes, heavily pre-treated to remove debris, and then pushed under extreme pressure against specialized membranes. Those membranes act as an incredibly fine microscopic filter. The pressure forces the water molecules through, separating them out as pure, drinkable water. It is a cleaner, highly scalable way to keep the expanding city alive. For a moment, looking at a facility like Halcyon, it feels like a complete engineering triumph. The extraction technology is getting much better, the energy source is getting cleaner, and the daily output volume is increasing significantly. It appears that Dubai has already solved the next major problem of urban expansion. But there is a physical reality to reverse osmosis that no amount of operating efficiency can erase. More efficient desalination does not make the other water disappear. Every single gallon of fresh water produced by a desalination plant has a second side. While the pure water is pumped inland to fill rooftop tanks, irrigate landscaping, and supply the expanding urban grid, everything that the membranes rejected is pushed in the opposite direction. This reject stream is a highly concentrated brine. It contains all the salts and minerals that were forcefully stripped out of the fresh water, making it significantly saltier, denser, and often warmer than the ocean it originally came from. Producing a few million gallons of this concentrated brine is a highly localized, manageable engineering challenge that coastal cities have dealt with for decades. But you have to remember the baseline scale we are dealing with. Dubai already has over 555 million gallons of daily production capacity, and it is building massive facilities like Halcyon to push that number much higher. This process does not pause for a single minute. The outfall pipes operate continuously, discharging the rejected brine back into the Arabian Gulf every hour of every day. When a single desalination plant produces brine, it is managed through carefully designed outfall pipes that attempt to disperse the reject water back into the open sea. But what happens when desalination capacity across an entire region keeps growing at an accelerated pace year after year? The story is no longer simply about whether engineers can produce enough fresh water to sustain an expanding metropolis. The story expands to a much larger scale. It becomes about what happens to the body of water that has to continuously absorb the industrial byproduct of all that survival. To understand the true consequence of scaling up this water machine, you have to look at how that reject stream actually behaves when it leaves the discharge pipes. It is not just about adding more salt to the sea and assuming it will dilute instantly. It is about fluid physics. Because the reject stream from a reverse osmosis plant is highly concentrated, it is physically denser and heavier than the surrounding seawater. When it is pumped back into the ocean, it does not immediately mix evenly into the upper waves. Instead, that dense, heavy liquid has a strong tendency to sink. It moves downward, where it can accumulate, influence bottom water behavior, and alter local underwater currents. When researchers model the coastal impacts of desalination across the Arabian Gulf, they look closely at these specific physical dynamics. Studies indicate that under high-volume discharge scenarios, the continuous output of dense brine can lead to meaningful changes in salinity and temperature near certain parts of the Arabian coast. This heavier layer can hug the seafloor, potentially exposing the marine environments immediately surrounding the outfall zones to conditions that are noticeably different from the open ocean. The continuous, relentless operation of these massive coastal plants creates a steady influx of heavier, saltier water into the shallow marine zones. As you look at the sheer scale of future facilities like Halcyon and realize that the city is preparing to extract hundreds of millions of additional gallons of fresh water, a logical conclusion starts to form in your mind. You picture a closed system where all the extracted fresh water goes inland and all the rejected salt simply piles up on the seabed forever. The visual image is incredibly stark and immediately concerning. It feels like a guaranteed trajectory. You start to assume that every new plant built along the coast is just another step toward making the regional sea too toxic to support life. If desalination capacity keeps expanding at this rate, isn't the entire Gulf eventually going to reach a tipping point and collapse under the weight of its own salt? It is an incredibly easy assumption to make. If multiple coastal plants are constantly discharging dense, concentrated brine, it feels like the entire basin should be steadily turning into an unlivable, ultra-saline lake. But the Arabian Gulf is not a sealed bathtub slowly filling up with salt. The physical reality of the ocean is far more complex than a simple container. Recent oceanographic research modeling desalination impacts across the Arabian Gulf has found a critically important nuance to this assumption. While it is entirely true that dense saline water influences bottom circulation and raises salinity near discharge points, the Gulf itself is a highly dynamic body of water. There is a massive, ongoing exchange of water through the Strait of Hormuz. Researchers note that the ocean's large-scale circulation can actually buffer a significant part of the basin-wide salt accumulation. The currents actively export heavier, saltier water out through the strait and into the wider Arabian Sea, while pulling in fresher ocean water to replace it. This means the basin as a whole is not simply accumulating salt until it becomes completely barren. Therefore, the scientific story is not a simplistic countdown to an entirely dead Gulf. The ocean has an immense, natural capacity to process and cycle some of that industrial byproduct, preventing a uniform, basin-wide disaster. But this scientific reality does not eliminate the problem of concentrated brine. It simply corrects our understanding of it and tells us that we have been looking in the wrong place for the primary threat. The surprising part is that this circulation does not make the environmental challenge disappear. If the entire basin is not facing imminent ecological collapse, it changes the nature of the risk. Instead of looking at the center of the Gulf, we have to look at the edges. The most intense pressure from a massive desalination network does not happen hundreds of miles out in the deep, circulating water of the Gulf. The pressure happens exactly where the water is being drawn in and pushed back out. It happens much closer to shore, right where the city meets the sea. When you reframe the threat from a basin-wide collapse to a localized coastal challenge, the stakes for a city like Dubai become immediately clear. Look at the famous coastline. The pristine tourist beaches, the luxury waterfront resorts, the intricate engineered fronds of the Palm Jumeirah, and the expanding marine developments all exist in the exact same shallow coastal environment that supports the city's massive desalination infrastructure. They share the exact same water. And it is in these shallow, near-shore environments where the physical consequences of reject brine become most pronounced. Because the heavier saline water sinks, local discharge areas bear the absolute brunt of the temperature and salinity changes. This localized physical dynamic creates a cumulative pressure on sensitive marine ecosystems that exist right on the city's doorstep. Now, there is no current evidence to suggest that specific tourist landmarks, famous beaches, or iconic resorts are being directly degraded by a particular outfall pipe today. The beaches are not dying, and the resorts are not failing because of the utility network. But as the city engineers an even larger water production system, the sheer volume of concentrated reject water has to be carefully managed in a highly developed, highly valuable coastal zone. You cannot simply hide hundreds of millions of gallons of heavy brine when your entire tourism and real estate economy is built on the pristine appeal of that exact same shoreline. The engineering challenge is no longer just about making enough water to keep the desert green and the towers functioning. It is about aggressively managing the localized coastal footprint of that survival. Planners have to ensure that the infrastructure keeping the city alive inland does not inadvertently compromise the shallow marine environment that makes the city economically valuable. The pressure builds exactly where the real estate is most expensive. Local circulation, advanced outfall design, and continuous ecological monitoring become critical lines of defense against local environmental stress. They have to balance the output of massive industrial facilities like Hasian against the health of the immediate recreational shoreline. And that localized coastal pressure becomes infinitely more complicated when you pull back from the city limits and realize that Dubai is not acting in isolation. If you pull the camera back from the Dubai skyline and look at the wider region, a much larger scale question emerges. Dubai's individual expansion of desalination capacity might be a highly engineered, well-managed process on its own. But Dubai is not the only economy on this coastline solving its fundamental water scarcity by engineering the ocean. Follow the shoreline on a regional map. From the rest of the United Arab Emirates, up through Qatar, Bahrain, Kuwait, and along the massive eastern coast of Saudi Arabia, almost every major urban center is reaching for the exact same technological solution. They are all building their own giant water machines. When researchers look at the trajectory of the entire region, the long-term projections are staggering. One peer-reviewed study noted that freshwater production from desalination across the Arabian Gulf could increase by more than sixfold by the year 2050, relative to current production levels. That projection does not mean Dubai alone will increase its capacity sixfold. It means that an entire region is simultaneously accelerating its seawater extraction and brine discharge. While the Strait of Hormuz provides a vital buffer for the basin, this level of cumulative expansion creates an unprecedented management challenge. When multiple expanding cities, industrial zones, and growing populations all rely on the same body of water to act as both their primary reservoir and their industrial disposal site, the local pressures stack up. A highly efficient, localized system works perfectly when it stands alone. But what happens when an entire coastline of booming megacities pushes the same technological solution to its absolute maximum capacity at the exact same time? The risk is no longer just about one outfall pipe altering a few miles of local coastline. It is about the combined, overlapping footprint of dozens of massive facilities, all operating at peak capacity, sharing the same shallow gulf. It forces you to ask, what happens when the cumulative weight of regional survival outpaces the ocean's ability to dilute the byproduct locally? That scale of shared reliance completely redefines the water security challenge. This brings us directly back to the massive scale of the machine Dubai is building right now. The baseline capacity of 555 million imperial gallons a day is already a staggering engineering reality. But the utility authority has clear, verified targets to push that ceiling significantly higher. With expectations for another 120 million gallons of reverse osmosis capacity during 2026, and the massive Hassian project designed to eventually reach 180 million gallons a day, the future water grid is moving toward an unprecedented volume. These numbers prove one very clear point. Dubai is not preparing to reduce its reliance on desalination. It is preparing for desalination to remain the absolute, non-negotiable foundation of its future water security. The new infrastructure represents vital and necessary technological progress. The accelerating shift toward seawater reverse osmosis and the integration of cleaner energy sources will undoubtedly make the entire production network more efficient than the legacy thermal plants of the past. It is a smarter, more sustainable way to manufacture water for a desert environment. But there is a fundamental distinction that has to be made when looking at the future of the city. Improving the internal efficiency of the machine is not the same thing as eliminating the external consequences of making the machine significantly larger. A cleaner plant still rejects concentrated brine. A more efficient membrane still requires vast amounts of seawater to function. Dubai is successfully engineering a way to produce more pure water than ever before, but doing so means it must simultaneously manage a much larger industrial footprint right on its own shoreline. The paradox established at the very beginning remains true. The technology absolutely works, but as the solution expands to meet the demands of a growing metropolis, the challenge of managing what gets left behind simply scales up alongside it. Desalination works. That is precisely why a growing city like Dubai continues to invest billions of dirhams into expanding it. But every time an engineered solution successfully overcomes a natural limit, it simply moves that limiting factor somewhere else. The original limitation was a severe lack of fresh water in the desert. The potential future limitations are the massive energy required to run the membranes, the coastal management of the heavy brine, and the resilience of the shallow marine ecosystems living right next to the outfall pipes. You can always build another massive plant to solve the immediate scarcity of water. But at some point, as the infrastructure scales into the billions of gallons, the most critical question changes. The question is no longer simply about how much more fresh water the city can possibly produce. It is about how much water the future city will actually need to consume. Because eventually, you have to ask, does the next great breakthrough in long-term water security come from building an even bigger desalination plant, or from building a city that needs less water in the first place? This video is for educational and analytical purposes, examining coastal desalination engineering based on current data. It is not a definitive ecological forecast. What is the ultimate limit for cities relying on desalination? Share your thoughts below, and subscribe to the channel as we explore the infrastructure powering the modern world.